Hey everyone, in this video I'm going to go through questions 55 through 60 of the USNCO 2025 local exam. This is the organic chemistry / biochemistry part of the exam, and you can follow along with both the test and the solutions document I've written in the description below. So let's start off with question 55. It's asking what the relationship between the two alcohols is. And we can first figure this out by realizing that this wedge here means the OH is out of the page. So it's going to be towards you, and this dash means this is into the page this time, or away from you. So I think this is fairly intuitive, but if you rotate this molecule on the left 180 degrees across this direction, you're going to get this OH group that was previously out of the page into to get that into the page. So and this 5-carbon structure is going to remain the same. So the OH group is going to flip to this position, if that makes sense, or rather this position, and it's going to go from out of the page to into the page because of the rotation. So our answer is going to be identical, since we can transform the molecule on the left into the molecule on the right. Let's move on to question 56. So question 56 is asking in the molecule below how many sp2 and sp hybridized carbons are there. So sp2 carbons are going to be carbons with a steric number of 3. And all that means is that the number of atoms it's attached to plus the number of lone pairs it has is going to be 3. And for sp2, the steric number, or sp, the steric number is going to be 2. It's a bit messy. But yeah, it's going to be a steric number of 2. So that just means that the number of atoms it's connected to plus the number of lone pairs it has is going to be 2. So immediately we can see this triple bond here. And a triple bond is a huge indicator of an sp hybridized carbon. This carbon here and this carbon here are both going to be sp. So we're looking at 2 sp hybridized carbons. And if you look at the more intuitive way of representing it here on the right, if you're not familiar with the dash notation, you can see that this C is attached to this carbon, and this carbon is attached to the carbon here and the hydrogen here. So both of them have a steric number of 2, and they're both sp hybridized. So we have 2 sp hybridized carbons. If we look at the answer choices, there's only one answer choice that has 2 sp hybridized carbons. So that's going to be our answer. But I'm also going to quickly identify the sp2 carbons for anyone who's trying to learn. So the sp2 carbons are going to be the ones with the steric number of 3. So double bonds are also a great indicator of sp2 hybridized carbons. And we can see in this ring here, all 6 carbons in this ring are going to be sp2 hybridized. If you're confused because these are attaching to 2 carbons, remember there's a lone pair on each of these. I'm not going to draw it up fully, but you get my point. And for cases like these 2 carbons, they're attached to 3 other atoms. So they all have a steric number of 3, so they're all sp2 hybridized. And in fact, we do have 6 as the answer to verify. So that's going to be our answer, A. Let's move on to question 57. So question 57 is asking us to describe the most stable conformation of cyclohexane. And if you know this off the top of your head, this is like a 5-second question because you know about the chair conformation of at cyclohexane. But if you don't, I'm going to go through how to reason it out. So answer A is telling us that all 6 carbons are in the same plane, or they're planar. So it would form like a hexagon like this. That's pretty bad hexagon. But if you know your interior angles, you know this will be 720 degrees of interior angles. So each CC angle is going to be 120 degrees. And we're looking for that ideal around 109.5. So that's not going to be good because that's going to have a lot of angle strain. Or in other words, it's going to be deviating from the ideal angle quite a bit, so it's not going to be the most stable conformation of cyclohexane. On the other hand, like I just mentioned, you want bond angles to be 109.5. And you might be wondering how that's possible with cyclohexane, and that's because of something called the chair conformation of cyclohexane. So it's a bit hard to understand like 2D wise, but you can see that this is cyclohexane with 6 carbon atoms, and it forms this chair type of conformation. There are 2 possible chair conformations, but they all have a CCC bond angle of 109.5. And in case you don't know about the chair conformation of cyclohexane, I'm going to go over the other answer choices to show why you can use elimination to solve this problem as well. So answer C is telling us that the hydrogens are eclipsed rather than staggered. So if you don't know what that means, I think you can kind of tell from the names, but I think you probably should know what they mean for this section. These are going to be eclipsed hydrogens, so you can see how they're on the same axis here. 1 carbon here is in the front, 1 is in the back. So yeah, you're going to see how these hydrogens are on the same axis. And meanwhile, over here, you can see how the hydrogens are staggered. So the carbons are still in the same position, but the hydrogens have sort of rotated so that the nearest distance between them is 60 degrees here. And the reason why staggered hydrogens are going to be more stable is because you're going to have less electrons repelling each other. Like these electrons in the pair here, or in the bonds here, they're going to be repelling each other less because they have a greater distance between them, a greater angle between them, compared to the eclipsed hydrogens here, which are quite close together and have a lot of electrons repelling each other. So we can eliminate that as well. I'll just update our answers here. We've eliminated this, we've eliminated this. And as for D, this is kind of a nonsensical answer. It's telling us that the carbon-carbon bonds are going to be different, but we know that they're all like single bonds, and if they were different, it's going to be like angle strain and a whole bunch of other things. You're going to disrupt the geometry of the molecule. So you can kind of tell just by reading this that this is kind of a nonsensical answer. The bonds are all identical, so we can eliminate this as well. And their answer is going to be B. Even if you don't know about the chair conformation of cyclohexane, which you should know about, you can still solve this problem through elimination. Now let's move on to question 58. So question 58 is describing this mechanism. I'm not going to read it out, but let's draw it here on the right. So 2-methyl-2-propanol, which is going to be this right here. Remember to practice your nomenclature. Is going to react with aqueous concentrated hydrochloric acid, and it's going to go to 2-chloro-2-methyl propane. So that's going to be this right here. So immediately from just drawing the mechanism, you can already tell that this is going to be a substitution. This OH group here is going to get protonated when this HCl is going to split up into H plus and Cl minus. It's going to get protonated by this H plus, and that's going to be a leaving group here. So this is going to leave, and this this chloride anion is going to come in and replace this OH group, and you can see that in this molecule here. The Cl has taken the OH's position. So you can immediately tell that it's already a substitution, and in case if you're unsure, look at the temperature that this reaction is proceeding at. If you know the difference between elimination and substitution, eliminations typically proceed at higher temperatures because they have a greater entropy and you use Gibbs free energy. So yeah, this elimination is going to be an unlikely mechanism here, and it's not going to be the correct answer. So we can eliminate C and D. Now let's discuss the difference between SN1 and SN2. So SN1 is going to proceed in 2 steps, and SN2 is going to proceed in 1 concerted step. So the reason why this is not SN2 is because this carbon is tertiary, or rather when it forms a carbocation, it's going to be tertiary. So that means there's simply not enough room for it to happen in 1 step. There's no room for a backside attack from the chloride anion here. In more technical terms, the carbon is going to be sterically hindered, and that's just a fancy way of saying there's no room for this to happen in 1 step. So first the leaving group has to leave, and then the chloride anion is going to substitute in. So our answer is going to be A. Okay, let's move on to question 59. So question 59 is asking about the properties of ketones and esters. So let's go through this answer choice by answer choice. So first, let me actually draw ketones and esters. I think it'll be helpful here. So this is going to be what a ketone looks like. That's our ketone. And then an ester is going to be very similar, except it has an O here, but this double bond is still the same. So we can see just by looking at the molecule, there's no real source of H+. There's no like OH or FH or something that would release a hydrogen easily or a proton easily. And so we're looking at we're looking at CH as the only source of H+, but CH carbon won't likely give up an H+ because it's just going to be more unstable, and that's only going to really happen in extreme environments. So pretty much neither of these function like acids. So we can eliminate A for now. Now let's move on to B. So it's saying that ketones are going to react through nucleophilic addition, esters are going to react through nucleophilic substitution. And this is true. In the case of ketones, the nucleophile is going to attach onto here, and two of the electrons in the double bond are going to go up to the O, and it's going to have 3 lone pairs, and the nucleophile is going to attach. So it's going to look something like this here. There's going to be a negative charge on the O. This stuff is going to remain the same, and then you'll have the nucleophile here. And the nucleophile is contributing these 2 electrons to the bond. So we can say that ketones definitely react via nucleophilic addition. How about esters though? So esters, this is going to function as a leaving group. So this is going to leave, and the nucleophile is going to come in here. So yeah, esters are going to react via nucleophilic substitution, and we can easily see that because of this leaving group here. So our answer is going to be B, because both parts of that statement are correct. But I'm also going to go through the other answer choices. So ketones are readily reduced, esters are readily oxidized. One part of that statement is true. Ketones are readily reduced. Let me just go through like the chain of oxidation of alcohols. We have primary alcohols. They get oxidized into aldehydes and then carboxylic acids. And secondary alcohols are going to get oxidized into ketones, and tertiary alcohols are not going to be oxidized very easily. So ketones can be readily reduced. That's just a reverse of this. They're going to turn back into secondary alcohols. And as for esters, there's also another pathway. Primary alcohols through, I believe it's Fischer esterification, can turn into esters, or can be oxidized into esters. But from here, they're not going to be able to be oxidized again. They can be reduced into primary alcohols, but not oxidized. So our answer is not going to be C, because the second part of the statement is not going to be true. And as for D, carbonyl groups in general are going to be resonance stabilized. Just like by definition, this can have resonance with a positively charged carbon and a negatively charged oxygen. So all carbonyls, regardless of the molecule, are typically going to be resonance stabilized. So D is not going to be our answer, since it's saying that the carbonyl group of an ester is not resonance stabilized, which is not true. So our answer is still going to be B. Okay, this is the very last problem of the exam. If you've been following along with the playlist, you've seen all the solutions now, so that'll hopefully help you prepare for the 2026 exam. But yeah, let's hop into the last problem. Okay, so it's asking which is not found in a typical nucleic acid. And it gives us 4 answer choices. So unfortunately, this is an incredibly hard problem to reason out. You pretty much just have to know this, and if you don't, then I guess just try to guess something. If you look at, if you can, you know that DNA is a nucleic acid, and if you know like the general structure of DNA, you might be able to answer this. Essentially, DNA has these bases here, which are going to be A, T, C, and G, and those are going to be heterocyclic bases. So we can see that C is found in a typical nucleic acid. It's asking for what's not found. So let's go again. We also have a sugar phosphate backbone, so that's going to involve 5-carbon sugars and dialkyl phosphates. So both B and D are incorrect since those are found in DNA, a typical nucleic acid. So through process of elimination, we have A. And of course, you actually need to know the structure of DNA or something to be able to solve this problem. Otherwise, it's pretty hard to reason it out. If you look at the solution, reasoning it out is basically just knowing the structure of DNA. So yeah, that was the end of the exam. Hopefully you enjoyed this series, and thank you for watching.